Welcome to the weekly M-Cube seminar. Today our speaker is Steve Shkoller. Steve is a distinguished professor of mathematics at the University of California, Davis. He was a professor of mathematics at the University of Oxford and a fellow of Trinity College. He's a fellow of the AMS, and that's the American Mathematical Society. Not our AMS, American Meteorological Society.
That's the same thing we say about you.
Yeah. So Steve works on the analysis of the Euler equations of hydrodynamics and related fluid models. He established the first theorems on multidimensional shock formation and shock development for Euler equations, and analyzed the motion of free surface flows, vortex sheets, contact discontinuities, and fluid structure interaction problems. This analysis has led to the development of new computational methods for gas dynamics and combustion problems, fast interface models for Rayleigh-Taylor type instability, and novel adaptive meshing schemes for flows with complex small-scale structures. And today's title of the talk is Fast Interface Models and Adaptive Meshing for Flows, for Multiphase Flows, parentheses, for clouds and plumes, in case you're thinking otherwise. Right. Hey, Steve.
Thank you very much, Rich. Thank you very much to the organizers for the invitation to speak here. It's a great honor for me to be able to tell you a little bit about what we've been up to, and mostly I'm trying to learn what kind of interesting questions your area has that maybe applied mathematicians can get into and answer. And the clouds and plumes is very parenthetical, so let's see where we're at. So I'm going to give you a talk that contains two parts. The first 2/3 roughly will be on what I call fast interface models. Is this on? Everything working okay? Okay. These fast interface methods are model equations for the Euler equations, and they're designed to simulate the flow of contact discontinuities, vortex sheets, shock waves, what have you, in a way that reduces the dimension and makes the computation extremely fast, orders of magnitude faster than a traditional solution strategy. This part is joint work with a PhD student named Gavin Pandya, who I'm told is very interested in coming to Boulder at some stage. The second part is what I call smooth adaptive mesh refinement. This is basically because there are complex flow regimes in which these interface models can move geometry around, but then certain reaction chemistry and other complicated flow features, one would like to still have some adaptive mesh concentrated around this very, very tricky geometric flow. And this is where a new way of doing this comes into play. It's also quite fast, and it's very, very easy to implement. So I'll explain that. And that is joint work with another PhD student named Rag Ramani. So this isn't so important, but if anyone is interested in, after the talk, if anyone decides they're interested in anything, these would be the papers one could refer to, and they're all available on my website. Okay, so here's where we begin. Most of what I'll talk about in the beginning of this talk, having to do with these fast interface models, has to do with the Rayleigh-Taylor instability and the type of small-scale structures that are being created. So in the models that I'm creating, there will be no viscosity per se, no dissipation mechanism. So interfaces will be kept sharp. And in this class of problems of Rayleigh-Taylor type, when you have no viscosity that inhibits the small-scale formation, the more cells you add into your problem, you're going to get smaller and smaller small-scale structures forming. And I will also discuss how diffusion can be modeled. But the point being is this is the kind of structure we would like to capture in a very nice way. And the two ideas that enter the mix is that we're going to start with the Euler equations of hydrodynamics. We're going to reduce the velocity field into sort of component parts in which we can then reconstruct the global velocity field from information on these geometric interfaces. This will give us the ability for what's called dimensional reduction. So if you're thinking of a three-dimensional fluid flow, we'll reduce the discretization to a two-dimensional problem. And then in addition, the resulting system when obtained is still the Euler equation in some sense, and it's still too complicated. And so we introduced a new method that we call call asymptotic approximations in the non-locality. So usually when you think of classical asymptotic theories for, say, water waves, they're usually small.
There's just one comment from online to stay near the microphone.
Oh. Okay. Sorry about that, online people. So usually when you think of asymptotics, you think of small amplitude, small slope. That is entirely the wrong regime for the kinds of problems we're interested in. You can envision that a picture like this you cannot model with a system that's limited to small slopes, for example. Okay, so let me continue. This is kind of the picture to start with. So this is a contact discontinuity or a vortex sheet, which means that how I want you to think about this is that this is a material interface separating fluids of two different densities. They don't have to be constant density, but you can think of it as being some density rho plus on top and density rho minus below. And you have the full Euler equations here. So you have conservation of mass, conservation of momentum, and conservation of energy. And what forms this surface of discontinuity is that you have a jump in the tangential components of the velocity field, whereas the normal components of velocity remain continuous, as does the pressure. A shock discontinuity is very different. It moves with a different velocity. It has different jump conditions. But these are examples of the kinds of interfaces that I want to create models for. And the idea is that, here's a simple example, that if you knew the vorticity and the compression of your fluid, you could reconstruct the velocity field by effectively inverting the Laplace operator. Here in 3 dimensions, the Laplace operator has this particular representation. The inversion of the Laplace operator is this particular representation. This is a generalization of what is known as the Biot-Savart law. And you can restrict the vorticity and the compression, which I'm calling chi here, you can restrict them to be measures that just live on hypersurfaces. So you don't have to have vorticity defined in the bulk, for example. You can have it defined on that complicated surface, and you can reconstruct the velocity everywhere using a formula of this type. So here's the idea. Let me just sort of explain. Here's a way of writing Euler that's a boundary integral formulation. And again, it's not essential to have incompressibility and irrotationality, but if you like, you can think of the fluid as being irrotational and incompressible with vorticity being concentrated on this vortex sheet. So what this boundary integral formulation gives you, and I'll be precise with what this is on the next slide, but as I said, it gives you dimensional reduction because instead of having to discretize 3-dimensional space, you only have to discretize a surface. It has this Lagrangian type of feel to it in that the parameterization for this surface, it sort of naturally clusters points where all the action is. So it has this kind of natural mesh propagation, which behaves nicely, but we still add some adaptivity to the problem if necessary. That's the upside of this scheme. The downside is that when I actually write for you what the Euler equations look like in this boundary integral formulation, you will see that they are horrifically complicated, and there's one particular term which makes the computation almost undoable. And to my knowledge, no one has done a good 3-dimensional computation of those exact equations. So I'll point that out in a moment. And as I said, what happens is that you leave the realm of having 5 equations for mass, momentum, and energy which are defined on a 3-dimensional space and time. to just evolving three components of the parameterization z. So every curve, every point on that particular surface is just z1, comma, z2, comma, z3, three coordinates. And the amplitude of vorticity, also known as the vorticity measure, this is effectively the jump and the tangential components of velocity. So it has two components. And this measure lives on that complicated surface and only requires two unknowns, again, only as a function of two independent variables rather than three. So this is a horrific slide. Don't get scared. I hate it myself. The only reason I'm showing it to you is, okay, this is the full Euler equations without any approximation, at least in the case where you have constant densities above and below the material interface. And does this have a?
It's better to use the pointer on the screen for folks at home.
Point, oh, okay, great. I didn't even think of that. So this term here, so these are basically, this is the Biot-Savart law. This is essentially telling you what the velocity is doing along the surface. This is looks like a pretty complicated thing, but this part really, these first three equations aren't actually that bad to solve. What's complicated is that these components of vorticity, W1 and W2, they have a very complicated evolution equation. And the complication is that it's the usual time-dependent evolution, but then you see that there's a time derivative here acting on velocities themselves. So this term here and this term here becomes exceedingly difficult to try and solve for in a stable fashion in 3 dimensions. In 2, it can be done. In 3, it's rather difficult. So this is what I'm saying is the bad term. This is this term here written in vector notation with a scalar product. So that's this term here. And when you expand it out using the Biot-Savart law, the evolution equations for the z themselves, you see that you have these really horrible terms here where this time derivative is sitting on the derivative of the z, and this becomes extremely difficult to solve. You need, as I said, to my knowledge, no one has successfully solved this equation. So the motivation here is that the idea is nice for dimensional reduction, but you have to go further if you actually want something useful. So what you do is you go back to these equations and you play a game of asymptotics. And what becomes small here is non-locality. So what non-locality means is, this is like, imagine you have a bowl of Jell-O and you stick your finger in the Jell-O, the whole thing will jiggle. It doesn't have local finite speed of propagation the way acoustic waves do. And so what you'd like to do is say, well, this kernel, it decays kind of fast. And then you ask yourself, how important is really distant neighbor interaction? And you play this game of asymptotics where you do this expansion and how much information you're allowing to enter the game from very far away at the point you're evaluating. And when you do this, you get a hierarchy of models. So this slide, again, this is maybe the last ugly slide I'm going to show you, so just bear with me. This is just to say that you do basically Taylor expansions in all variables, in all geometry, and you try and identify structure. And you're trying to identify certain curvature terms, you're trying to identify certain non-local operators like the Riesz transform, the Hilbert transform in lower dimension, things like this. And when you do this, you get leading order approximations of that full mess that I showed you. And you get a sequence of models. I call them the lower order Z model, the medium order Z model, and the higher order Z model. The lower order Z model almost becomes a local evolution equation. So this is telling you that you need some law. Partial t of z1 is some velocity, u1. Partial t of z2 is some velocity, u bar 2. Partial t z3 is some velocity, u bar 3. and you replace these exact velocities coming from this full non-local reconstruction with some approximation. And in the lower order Z model, the approximation is given by this vector nu, and nu is almost local. The only non-locality comes from what's called the Riesz transform. And this gives you a very, very fast and accurate model if you're interested in the envelope of the behavior, where by envelope I mean it's going to be a surface that covers all of the small scale features inside of it. Okay, so that's the lower order model, and if you continue in the expansion, you get, so this is just how you write this lower order model in sort of expanded form. And then if you continue in the expansion, you get the medium and higher order models. So let me see if this is a video or not. Okay, so this is a video. This is just the lower order model. And what you'll see is that it does okay. It doesn't have tremendous amount of roll-up, and I'll explain to you why in a moment. But it does relatively well, and it's super fast at capturing sort of the envelope of behavior. And then you can go to the medium and higher order models. The medium order model continues to use this simple velocity field and the evolution of the vorticity, but it uses the real Biot-Savart velocity to move the interface. And in the higher order model, which is almost everything I'm going to show you is going to be with a higher order model, it uses the real Biot-Savart velocity to move everything, move the interface and in the vorticity. And it turns out that this is, I'm missing time derivatives here, I apologize, but it turns out that this is an incredibly good approximation to the full Euler dynamics, as I will show you in a moment. Okay, so it's an interesting question as to what creates this roll-up in the Rayleigh-Taylor instability and the Kelvin-Helmholtz instability. And what I'm showing you here is this is what the vorticity concentrated on this surface actually looks like. On the top row, it's the lower order model, which is like this envelope, and it doesn't roll up very much. And in the bottom row, it's the higher order model, which has great roll-up. And what causes the roll-up are spikes on this surface vorticity measure. This approximation where you have sort of removed non-locality almost entirely, the downside to that is it eliminates small scale structure because it doesn't allow the vorticity to spike as extremely as it should, whereas in the higher order model, it does exactly what the real solution does, and you can capture unbelievable structure. Okay, I'm going to skip this. That's desingularization. So here's an example of what you can do. So on the left, it's just the classic Rayleigh-Taylor problem. You have a heavy fluid sitting on top of a light fluid, and you perturb a flat interface a small amount, and you get this classic mushroom Rayleigh-Taylor roll-up. On the right, let me run that one more time. Oops. On the right, you have a little bubble rising into hitting another interface, and one will roll up into the other. And on the very right panel, I'm just showing you a zoom in, and you can see that this model, it doesn't care about how small the distance between the interfaces are. That distance in this particular simulation is like 1e minus 6, and it can get to as small as you like, and the simulation just doesn't care. And so I'll show you some comparisons with more traditional approaches, and you'll sort of see what you get out of this methodology. So here's a picture we took looking at the sky one day, and the purpose of this is just to say that, well, all of you know this, but this is sort of ubiquitous. But here, in one picture, it sort of looks like the cloud is giving you a sharp interface. And I sort of ran a little simulation just to sort of say, okay, yeah, you can sort of capture what looks like a sharp interface at that scale. Up above, you see there's a lot more diffusion, and it looks like it's been diffused. And using an ensemble of the same exact model, you can sort of capture that mixing or diffusion that's taking place in this top figure. This is a picture, this is a result that John Reisner actually asked me to do. Here you have a very light bubble that's rising in a stratified atmosphere. So you can see that the density gradient here, the vertical density gradient is negative, which is why eventually when the bubble starts to rise, it stops rising. And then there's a wind shear. I think in this simulation, I think I increased it something like 5 kilometers per second every 1,000 meters or something. And what you see here, again, no diffusion in this system. So if you've seen runs like this, sort of from traditional, like Eulerian, like John's high grad code, you would see that by the time you got to this third figure here, this would be extraordinarily diffused. But here again, what you're seeing is the pressure field is creating an incredibly small distance between the two adjacent interfaces. And in this run, it went down to something like 1e-7 or something like that. And this is just to say that you can really capture the fine scale structure. And these run, well, we'll talk about timing in a moment. So here's a video of this run, same run, but you can just sort of see the dynamics of what's happening here. Now, at this stage, you're probably thinking to yourself, well, okay, they're nice pictures, but does this have anything to do with reality, and is it of any use in what I'm thinking about? I don't actually know the question to the answer to the latter question, but to the former, I can actually show you results where we compared against both experiments and theory. So let me begin with these classical Rayleigh-Taylor experiments that were conducted, I think, in the late 80s by Reed and Youngs. So you take a container with heavy fluid on the bottom and light fluid on top, and you put it on a rocket motor, and you launch it. And this creates acceleration. And this was a very nice experiment. They were able to experimentally measure the growth rate of this mixing layer. This is sort of how the interface, how the two fluids of opposite density mix together and how the rate at which this layer grows. And there's also a theoretical prediction that is somewhat phenomenological. The prediction is that it grows quadratically with a certain parameter alpha that's roughly 0.06 or 0.07, depending on whether you're using numerical data or experimental data. And some people at Los Alamos improved upon this and let this theory become slightly dynamic. It's still essentially quadratic growth. So we used our interface model to simulate exactly this what's called the rocket rig experiment. And what you do is you take initial data where you perturb, your perturbation is random with Gaussian, it's a Gaussian random perturbation, and you basically randomly excite the amplitude of certain modes. And we did 100 simulations. Each simulation just takes a few seconds, so you can do 100 simulations and average over. And you can see the comparison is really quite good. So the dark gray is a very small standard deviation. The light gray is a slightly larger standard deviation, but the results compare really well with both their theoretical and experimental results. I think this is a video. This is a simulation of the rocket rig. This is one particular run. And if you do this 100 times and you take the ensemble of 100 runs where each run is initialized with this random perturbation, what happens is that you model the effect of viscosity acting at the same length scales at which you've randomly perturbed. So this is a cross-section of this ensemble of runs, and it looks very, very much like the snapshots from the experiment. Now you can improve this, you can make this, this rocket rig experiment even more exciting by tilting the tank by about 2 or 3 degrees. And the idea is that if you tilt this tank, you're going to flip over the fluid. So after the instability kicks in, the heavy fluid will then be on top of the light fluid. So first, you run this with random data. So this is a cross-section of the experiment. This is like a photograph of the experiment. And as I pointed out here, they note in their paper that this is just an anomaly from the imaging method. So you should ignore this. And this is our 3-dimensional run. So they look pretty similar. And you can see that this interface will literally flip over onto itself. Okay, now let's be a little bit more precise with these comparisons. So now we're looking at slightly more classical Rayleigh-Taylor experiments by Waddell and Jacobs and Wilkinson and Jacobs. So some are going to be in 3D and some are in 2D. So here you put 2 fluids in a tank, the heavier fluid on the bottom, and this time you accelerate the tank downward. So again, you're in this unstable Rayleigh-Taylor regime. And now you use some sort of laser-induced fluorescence. I think in this picture, they took a diagonal cross-section for the results I'm going to show you. So this was the 3-dimensional snapshot. I'm just sort of showing you that at least quantitatively the pictures look the same. And then this is the cross-section. So here I'm comparing the higher order Z model in red with the cross-sectional experiment at a pretty late time. And the comparison's pretty good. I mean, I don't know I don't know. I don't know enough about all these experiments to say whether this is really good, but it looks pretty good. So here are more snapshots, and here what you're seeing is a time history. So you start with the initial time and moving in time until the full instability develops. And here we're running the medium order Z model. Again, this is a 3D simulation, and we're just taking a cross-section, matching the cross-section from their lasers. And again, the comparison is quite good, but you can see it's not just some specific snapshot that I picked where things lined up well. It pretty much lines up through the entire dynamics. So you're getting good comparison, I would say. So this was the full 3D experiment. There's also this 2D experiment of Waddell-Jacobs. And here you see, again, this is the 2D higher order Z model compared with this 2D experiment. Again, snapshots in time allowing the instability to develop. And you're getting what I think is very good comparison with this. So this is, in some sense, one way of validating how close you are to the full Euler equations. And in my business, we believe the Euler equations really do cover the fundamental mechanism of fluid flow. So that's a plus. Okay, so I told you there's this hierarchy of models, lower order, medium order, and higher order. And this picture sort of demonstrates what I meant by envelope. So if you want to just run the lower order Z model because all you care about is the basic, say, growth of the mixing layer, and you don't so much care about the fine scale structure, well, you can do that, and it does a really good job of serving as the envelope dynamics. And if you're interested in this small scale structure, you can run either the medium or higher order model. They're essentially the same. There's not much difference. So I usually just run the higher order model. You get really good agreement. Let me just say something interesting from a mathematical perspective. So these problems, in the absence of viscosity and in the absence of restoring forces like surface tension, they are known to be ill-posed. So what this means is that you expect that if you slightly perturb your initial data, the ill-posedness means that this perturbation could grow exponentially. And moreover, it is known that solutions, as you keep refining your mesh and you keep refining your mesh, it is known that these solutions do not converge. They don't even converge in a weak sense. But there are structures that do converge, and this is in some sense convergence on average. So what can you expect? You can expect things like the spike and the bubble locations to converge. You can expect the location of the roll-up to converge. The radius of the roll-up, that converges. The center of the location of this cage spiral, that converges. And this is sort of how this is what you get out of refinement. What is the speed? I kept saying these interface models are fast. So here, for a particular Rayleigh-Taylor computation, I'm going to compare with a traditional Eulerian method for solving the Euler equation. So this is a two-dimensional run. Because we're doing this on our laptops, we can't even do the full three-dimensional run on our laptops unless we're using our interface models. And we're doing 128 by 512. So this is the time it takes for the lower order Z model. This is the time it takes for the medium. This is the time for the higher order model. And this is the so-called C method. This is the traditional Eulerian approach. So basically in 2 dimensions, to get that picture I was showing you, you have 12,000 times speed up for the lower order model and about a 500 times speed up for the higher order model over conventional 2-dimensional simulation. And the speed up is significantly larger when you go to 3 space dimensions. There's a way that you can speed up the computation of the velocity reconstruction using a fast multipole method. We downloaded a standard package, and it works incredibly well. And this shows that you actually get O of n complexity for this procedure. So it's already, what I'm showing you here is just using very naive numerical integration, and this is O of n squared, and you can speed this up greatly if you download some sort of fast multipole method. Okay, this is just an example of, I keep showing you stuff in 2D, and I want to convince you that we can do everything in 3D. So just 3 different regimes of bubbles rising, and you're getting slightly different roll-up, slightly different geometry. And that's just sort of for artistic effect. Mixing. So these runs are really fast. Most of the stuff I showed you in 2D is on the order of seconds. Most of the stuff I show you in 3D is on the order of minutes. And as I said, if you're interested in modeling diffusive effects, what you can do, instead of trying to add some sort of Navier-Stokes solver, what you can do is simply ensemble 120, whatever, 2,000 runs. It's really fast. You can do it, the full ensemble within a minute or 2. And you are effectively adding viscosity at exactly the scale at which you're adding random perturbations to your interface. There's no theorem I'm aware of at this stage for this, but this is in fact what's happening numerically. So you can see on the left panel, you have, the resolved sharp interface, and on the right panel you see the ensembles. And it gives you, we compared this to an actual Navier-Stokes solver with viscosity added at that scale, and it looks exactly the same. And here's sort of just another picture just sort of zoomed in as to what happens to the classic Rayleigh-Taylor mushroom. So this is sort of a question we've been discussing as to where does the correct answer actually live? How much fine scale structure do you want from a problem that is inherently unstable and will continue to add structure as long as you continue to add resolution until you somehow break that with some sort of viscosity, something that inhibits the transmission of small scale formation. Okay, so what I'd like to do now is just compare for you what happens when you run a traditional Euler solver on the left here. So this is a two-dimensional run again. This is a heavy fluid sitting above a light fluid. It's something like density 3 on top and density 1 on the bottom, with a slight cosine perturbation of a flat interface. And this is, for us, this is high resolution. 512 by 1024 on our MacBooks. This takes about 10 hours to run, 9 to 10 hours to run. And on the right here, I'm gonna use the same initial data for the interface model. And again, on the very right panel will be a zoom in. And what you can just see is, so this simulation takes, I don't know, a few minutes to run. And you get tremendous small scale structure. And there's really just no comparison between how much more information you're getting at these small scales from the interface model than from this, for us, very intensive traditional simulation. So that's 2 fluids with 1 interface. Let's go to 3 fluids with 2 interfaces. So here the red fluid is density 4, the green fluid is density 2, and the blue fluid is density 1. And again, so 2 unstable, both interfaces are unstable, and very small cosine perturbation. And here's what you get on the right. So again, this is 348 by 768 cells. For us, again, this is what we call somewhat high resolution. This, again, took about 10 hours. And it's a good run. I mean, you're getting nice roll-up, you're getting the nice structures here and so forth. Now, again, you can run the interface model with the same initial data. And again, this just takes a few minutes. And you're getting much, much finer structure. You can see the interfaces rolling into themselves. Again, no diffusion, so the interfaces are not allowed to penetrate one another. And again, the distance between the interfaces is extremely small. So if you were to try and get this kind of resolution using a traditional method, you'd probably need something like 100, maybe something like 10 to the 6th by 10 to the 6th or something like this, or use adaptivity. So this is an example of a bubble rising with stable stratification on the left and unstable stratification on the right. So the model can do as many interfaces as you like, and this number here, this number here, it starts out like in this run, we started out with a total of 1,024 cells, and then as the length of the interface increases due to roll-up, you can easily add cells to the problem, and you can very nicely capture the small-scale structure. So that's just to say that you can do stratified flows very nicely with this model. This is the least, not a very exciting slide in the sense that nothing's moving, but it may be of interest in meteorology because this is a slide that describes entrainment. So in this scenario here, you take a heavy fluid on top, in the middle you have a light fluid, and on the bottom you have a heavy fluid. So the top interface is unstable, the bottom interface is stable. So you might think that you're just going to get sort of an instability up here and that everything's going to remain very nice down here. But in fact, what happens here is that this heavy fluid starts to get entrained. And what I've plotted here are snapshots. So this first curve is at initial time. And then as you progress from left to right, this is as time evolves. So what this is sort of showing you here, if you look at this first curve, this is sort of saying this blue curve here, okay, here you have the heavy fluid, and then here's the light fluid, and then here's the heavy fluid again. And what happens is that this massive vortex is set up, and it starts to, that instability from that top layer creates such a strong vortex that it grabs that heavy fluid from the bottom and just sucks it up into this roll-up. And you can see that it's dragging this heavy fluid into the region where there was only light fluid. And this is extremely accurate. What I've plotted here is you subtract the heavy fluid, rho plus, from whatever density is actually sitting at the location. Then you divide by the difference, rho plus minus rho minus. Rho minus is the light fluid. And then you horizontally average. And then what's left is a function of the vertical direction z. And you plot this. And then if you rescale it by centering it at the peak and dividing the width by this half width, the half width meaning the width halfway up, you get the exact self-similar progression of entrainment that's predicted by theory. So the model isn't only, it's quantitatively matching the theoretical prediction. It's not just giving you the correct qualitative dynamics, it's actually giving you the right numbers. So far, I started out the discussion by describing what happens essentially to vortex sheets. But what I want to describe is an idea where you take the full Euler equation and you decompose it into a succession of simpler problems and then put it all back together. So here I want to generalize the motion of just a vortex sheet to that of a contact of a shock wave hitting a contact discontinuity and interacting. So you guys probably don't deal with that many shocks, I don't know, in the atmosphere, unless, no. But it's still fun. So what you do is you do a certain kind of asymptotics for same kind that I described to you. And now, instead of just having a parameterization for the contact or vortex sheet and having evolution of vorticity, you also have a parameterization for a shock wave, for a shock curve or a shock surface. And then the object that plays the role of vorticity on the contact discontinuity is played by this so-called local Mach number on the shock wave itself. And this is a closed system. The exact evolution isn't so important. I'm only writing it here to impress you. But then you can reconstruct the velocity field everywhere, again, using sort of a simple reconstruction algorithm. This is just these functions, which I don't expect you to remember at all. And here's an example of a classical experiment done by Haas and Sturtevant. So what you're seeing here in both the experiment and in the simulation, the orange or red curve is the shock wave. It's moving downward and it hits this contact discontinuity. So the initial shape of the contact is being drawn by this dashed line, and then the blue line is the deformation due to the effect of the contact. So what's happening is that the contact is the shock wave is producing baroclinic vorticity on the contact and changing its dynamics. The contact discontinuity has a jump in the density, which creates a jump in the sound speed, which then changes the motion of the shock wave. Now, in this experiment, you see it's actually quite a beautiful experiment. You see three different kinds of shocks. There's the forward moving or transmitted shock, which is this guy here. And so far, that's all we have put into our model. But there's also this beautiful reflected shock, and there's this sort of Mach stem kind of behavior occurring over here. And we're going to add this separation and reflected shock into our model. We just haven't done it yet. But what you can see is in terms of the shape of the contact, it's actually pretty good. And the shock wave, the transmitted shock also looks quite good. So again, this is a problem where instead of solving Euler in 2 space dimensions, you're solving a simple evolution equation in 1 space dimension. And it's extremely fast, and it seems to give you very nice results. So here's an example of a shock wave. So this is a shock wave moving through air and helium inside of the bubble. And in this case, air outside and freon inside the bubble. So here it's lighter and here it's heavier. So that's what happens in that configuration. And here, when it hits the heavier bubble, it's really going to initiate a Kelvin-Helmholtz instability. So this compares very nicely to what we've seen in experiments. So why am I showing shock waves in a meteorology seminar? This is just to say that the idea, as I said, is to be able to decompose the basic behavior of the Euler equations into these constituent parts which track geometry, and then you can reconstruct velocity, density, pressure, and then you would like to add effects like temperature and possibly chemical reactions and things of this nature. And the purpose of showing you that you can do shocks merging with contacts is just to say that you can actually model all of these things separately and then put them together in this particular manner. This is where we're at in the program. We're going to add these things in the next few months, these things I've described. So this is what I mean by generalizing interface models. So the next thing we're doing is we're adding bulk temperature effects. Instead of having to solve any specific equation, you can essentially have almost a closed form solution from a heat equation to give you very accurate temperature profiles. You can study the compressibility effects on a vortex sheet by adding a special Mach number variable that describes how compression is changing the shape of the mushroom, if you will. You can add reaction chemistry via fast transport coupling. And our goal, in some sense, why we wanted to have this conversation today is that we're hoping that this can be very useful in applications like wildfire modeling, cloud dynamics, and a host of other things that people at Los Alamos are interested in. So that takes care of what I wanted to say about interface models. Now I just want to briefly talk about smooth adaptive meshing. So in this program here, where you have these interfaces and geometries like this, for example, what often happens is that you'll have like a combustion or a chemical reaction that takes place, and there's this interesting zone that pops up very, very close to where the geometry is very intricate. And in this region, we have a multi-scale algorithm where we can lay down a full mesh that's geometrically adapted to these fine structures and solve one part of the problem having to do with chemical reactions in that mesh and couple it to a highly resolved mesh coming from these interface models. And that is, in some sense, the motivation for why I'm going to tell you about this adaptive meshing algorithm. Okay, so again, the objective here is to have someone give you information as to how they need a mesh to deform around fine-scale structure, and then in turn, you provide for them that mapping that takes, say, a uniform collection of nodes, maybe on a rectangular grid, and maps them to whatever geometry you want. And this usually requires solving some sort of nonlinear or elliptic equation. The state-of-the-art method when we started this was this sort of Newton-Krylov method for solving what's called the Monge-Ampère equation. And that's kind of what I want to talk about, is a new scheme for doing this. So here's the typical method. This is the typical problem you see. This is the Monge-Ampère equation. That's what MA stands for. So what happens is the following. You decide for whatever reason that you want your mesh to look like this. And you give me a rule that I'm calling a function g that says, okay, g is telling this node to be over here, this node to be over here. It's effectively giving you this particular picture. And what you want from me is a mapping psi, which will tell you exactly how this node moves over here, how this node moves over here, and so forth. Now, this is a very complicated nonlinear elliptic equation. Suppose we're in 2 dimensions, as this picture is showing you here. The gradient of psi is a 2x2 matrix, and then you take its determinant, so you have something quadratic in highest order derivatives. And this determinant, this Jacobian determinant, has to be given to this function g, which is the rule you've given me, but it's not g along this uniform mesh, it's g along the deformation, which you still don't know. So the nonlinearity is entering in 2 ways. First, on the left-hand side, by virtue of its quadratic, in this case, structure. And then on the right-hand side, by virtue of the fact that you have to evaluate this function g on a collection of nodes whose locations you still haven't found. Okay. Now, the point is, I'm going to show you how to solve this problem by solving one linear Poisson equation, if you believe me. So first, a little bit of history. Peter Smolarkovich has worked on this with his students as well. There's essentially 2 approaches to this problem in the literature. The first approach says this is a complicated nonlinear elliptic problem. Instead of solving it directly, I'll embed it in a heat equation, and I'll sort of use a gradient descent to find an equilibrium to the heat equation, which will then be the solution to this particular equation. A second approach is to directly solve this equation by some sort of iteration scheme, and this goes under the name of Monge-Ampère optimization. And this is where you can use a Newton-Krylov solver, and to my knowledge, that was sort of the state of the art in this business. And the method I'm going to show you doesn't use either of these things and is at least 200 times faster than this Newton-Krylov method, which is a little bit faster than the moving mesh PDE approach, which is essentially a parabolic heat equation solve. So this slide is the algorithm for how you solve this equation here. So remember, you've given me the rule g, which is what's called the target function. It's where you want your nodes to cluster. So I'm going to solve this equation in this following way. Phi is a velocity potential. There's some velocity w bar, and it's equal to gradient phi. So I'm going to solve for gradient phi in the following way. I take your ruled function g. I say capital F is 1 divided by g. And then I solve this Poisson equation on the uniform mesh. Now, we solve this. You can solve this either we use a 4th order finite difference operator, but you can solve it in your favorite way, but you should have some accuracy to how you solve this. Okay, now once you solve for this potential function phi, you have a time-independent velocity field, w bar. And the idea, what's called the deformation part of this method, is that you create pseudo-time, fake time. You define a fake time that starts at tau equals 0 and ends up at tau equal 1. And in this fake time, you're effectively going to flow along this deformed velocity field, which now depends on this fake time. So it's the velocity field you obtain from this one linear solve. It's interpolated in this fake time kind of way. And now you can solve for the flow map, but this construction is chosen in such a way that you never actually have to do a Lagrangian solve. You do an Eulerian transport, which is really fast and requires no interpolation whatsoever. You solve this Eulerian transport for this function eta, which is defined for all fake times between 0 and 1. And then when you end up at time 1, that's the map psi, which is an exact solution to the nonlinear elliptic equation you began with. And in practice, around 10 to 20 iterations in fake time does the job quite nicely. So here's an example. the function g you gave me said, cluster all your points around a circle of, I don't know, radius, whatever, 0.4, 0.2. And what I've shown you here is the evolution in pseudo time. So it starts out without any deformation. It starts out at the identity map, meaning keep your rectangular mesh exactly where it is. And then you follow this transport along this fake velocity field constructed in this special way. And at time 1, you end up with exactly the mapping psi, such that when you take its gradient and then its determinant, you get exactly the rule you gave me evaluated along this perturbed mesh. So compared to other methods, we have fourth order accuracy. All these other methods are second order accurate. They could probably go to fourth order accurate, but that would be at extreme computational expense. And as I said, it's really fast. It's at least 200 times faster than this Newton-Krylov type scheme. There's a way now, so what I've shown you, when you only take, say, 20 pseudo time steps, and when you use a fourth order solver for the Poisson problem, that works really well if you have kind of a small deformation. But if your deformation is really large, then you would need to take more pseudo time steps and maybe even have more accuracy for how you solve your elliptic equation. So there's this new formulation that we created, which is called the it's a large deformation via a succession of near identity transformations. So now the idea is that you go one large deformation by breaking it up into 20 smaller deformations, each one of those small deformations computed in exactly the way I just showed you. So I'm not going to go into too much detail about this, but there's this very easy way where you create a subroutine using the algorithm I just showed you. And if you have a very large deformation, you basically call that subroutine 20 times to split the process into 20 smaller, close to identity transformations. And then you've computed that one large deformation, and then you can start again. So that's what this sort of entails, basically. And the idea of this scheme, it's the first perturbation algorithm I'm aware of where every single perturbation is solved exactly on the original uniform reference mesh that you began with. So it's not like you keep having to solve the problem on a new mesh. You're always solving the same problem on the same mesh, and the only thing that changes is the rule G that is given as how you contort the mesh. Okay, and this is just saying, okay, this is the sequence of how you get to this stage here by first computing a near identity perturbation and then taking the previous deformation that you had and composing with that transformation. Okay, so that's a little bit technical. Here's an example of the kind of thing you can do. So this is just following sort of a Rayleigh-Taylor kind of roll-up, and the mesh is contorting well enough where you can almost see the solution just by the mesh itself. Here's a real Rayleigh-Taylor problem. So here I'm going to we solve this first on a uniform mesh. So this is Rayleigh-Taylor 256 by 512. So what the red curve is the transport of the initial interface by this reconstructed velocity field. And in turn, what you see here is the way that the mesh is contorting to this computed red. Let me run it again. So the red interface is being computed by just transporting the initial interface using the velocity we're computing, and you can see how the mesh is trying to adhere to this fine scale structure. So what you can imagine is that if all of the action, if this was, say, the boundary of a cloud and you were having some interesting reactions taking place there, you can imagine that if you had a model that sort of produced for you this red curve, you could put in a mesh like this, which is localized just around where all the action is, and it doesn't take that many cells to really capture that interesting zone where all the action is happening. So again, this is 3 fluid, 2 interfaces. Again, we're going to capture it with our adaptive meshing. And you can see that the mesh, all of the cells here, so here you're getting a zoom in of about 15 or 20 to 1. And all the cells are really nice. They're like nothing loses convexity. And you get really nice solutions. So, so far I've given you the impression that you have to work on some sort of, rectangular mesh. You can work on any any reference mesh you like. The coordinate system doesn't matter, so you can, and dimension doesn't matter. This algorithm works equally well in 2 or 3 dimensions. It makes no difference. Now we've coupled this to an Euler solver using arbitrary Lagrangian Eulerian variables, and the ALE map is actually coming, oh, time? Okay, so let me skip all this stuff, and I just want to get to combustion. Okay, so this is a simple combustion model. I'm going to end in 2 slides. So this is a simple combustion model, and this is what happens when you add some reaction chemistry. So this is what the vortex sheet or contact discontinuity looks like when you have this sort of combustion taking place. And the edge of this blue region is what I call a pseudo-contact. And all of the mixing is taking place inside of this region here. And so this is exactly the motivation of the idea is that you can solve this with, so first the adaptive meshing can track both the contact and the pseudo-contact. And then you can solve this with adaptive meshing. So the first simulation I showed you was 800 by 800. This is 240 by 240 using our adaptive meshing, and it's 12 times faster than the original simulation. And it captures this highly unstable contact and all of the mixing zone quite accurately. So this is where I think there could be some interesting relevance to things in clouds. Okay, I've gone way over time. I'm going to stop here. Thank you very much.
A couple of questions? Comments?
Yeah, I'm really interested in those spherical bubble tests that you were doing, and wondering if you looked at how your solver might impact the kind of bulk properties of that bubble compared with traditional kind of 3D Eulerian solvers, specifically like the ascent rate of the bubble or its spreading rate horizontally, things like that. I'm wondering if there's much of an impact. There have been some studies that I know that have said there's some impact of viscosity on those kind of properties. That's I guess why I'm raising that question.
Yeah, so when we did this simulation, you're talking about when the bubble's rising in a stratified atmosphere with a wind shear?
No, well,
or just generally.
That was one example. I was talking even more general, like just unsheared, neutral environment, that kind of thing.
Yeah, so in the absence of wind shear and in the absence of massive stratification, the rate of rise is pretty comparable. That seems to compare really well. What the traditional solvers are missing are the fine scale structure. So in some problems, that fine scale structure starts to interact at larger scales. That's the kind of thing that you miss. When we run our traditional simulations, we have to add sufficient viscosity. And by the way, in our traditional simulations, when we're adding this sort of nonlinear viscosity, that viscosity is only being added tangential to the surface, to the bubble. Even so, you're getting enough diffusion where it's limiting how thin that bubble can get, and then it starts to smear out, and what it does over long periods of time is it can produce a breakup, a bubble breakup much sooner than in reality. And that's viscosity effects.
Okay, yeah, thanks.
As the simulation gets really complex looking, the interface gets longer and longer, are the time steps more and more expensive as it goes along?
We're actually using an implicit time stepper here. So ultimately, it does place some restrictions on the time step, but we're not using an explicit time stepper, so we don't have like a serious CFL problem, which allows us to go from, say, 256 to 5,000 cells without changing anything. So,
Can you speak into the mic?
oh, I'm sorry. Thank you.
Okay, I guess I'll take the last question. So when you do these ensemble experiments and you kind of simulate turbulent diffusion,
Yeah.
have you? I'm just wondering, does it have a? Would it have a Kolmogorov kind of scaling? Is like the flux through wave number space of energy, would it be constant, like in three-dimensional turbulent simulation of a grid-generated?
I actually have not checked the rate, but you do see a cascade, but I don't know exactly what the rate is. We haven't done such refined simulations with that ensemble in 3D. We've done it in 2D, but it's very different in 2D. It's not that interesting. But in 3D, you see a cascade. I just don't know what the slope is.
What the slope of the spectrum is.
Yeah.
Okay. All right. Well, thank you. Thanks again, Steve. Very interesting.
Thank you.